Hi everyone, welcome to lesson 10 of the Forces and Space Scheme of Work. This one's on floating and sinking. And it's not a lesson that goes into loads and loads of depth. We're not going to talk about Archimedes' principle and displacement of water and density and all of that stuff. The reason this is in the scheme of work is that it's a really nice, concrete example that stimulates or prompts students to think in terms of our two core concepts, one core concept in many ways, Newton's first and second law. This idea that if the forces are balanced, the object its motion doesn't change. If the forces are unbalanced, then the object's motion does change, and that's where it's using those ideas that we're going to explain floating and sinking. It's also a nice opportunity to revisit something we did in year 7, and if you didn't teach that in year 7, then it could be a good opportunity to just revisit the particle model again. I'm not going to go into loads of detail about that here, but there is a video available where I talk about how to explain upthrust in terms of particles. So what I would do first here is draw a boat, a really simple picture of a boat. So in fact, let me draw my boat first like that, and I'm going to draw the water. And what I'm going to do here is say, well, okay, I might revisit the reason we have upthrust, but I'm not going to go into loads of detail. The reason we have upthrust is because the particles are more densely packed down here than they are up here. This means you get more frequent collisions between the particles and the walls of the hull of the ship down here than you do up here. So you get a greater force down here than you do up here, or really it's a difference in pressure. But I'll put it as a kind of a greater force like this. So there's a bit of a, let's exaggerate this actually. The greater force down at the bottom than there is near the surface. And that's why, because there's kind of more of a push from the particles there than there is there, you get this force called upthrust. So what I'm going to do, I'm not going to go into loads of detail about the particles, and you might not wish to. It depends. If you want to revise that with the students, feel free. But what I'm really interested in here is this idea that, okay, here's the upthrust, like this. But of course, and I probably should have drawn this first, what force is acting downwards? Well, there's the force of gravity. And this is a diagram that students have drawn before, like this. Now, the point is, when the ship is floating, let's say our gravitational force, the weight, is equal to, I don't know, 1,000 newtons. Well, the point is that when it's floating, the upthrust will be equal to 1,000 newtons. And what you might want to do here is just model the process that we went through last time. It doesn't really matter what direction we take, although given we're going to look at sinking next, I might take downwards as positive. So I'm going to take that as positive like that. What I can do here is say, well, look, in this case, when the forces are balanced, then my resultant force is that's positive, so I'm going to do plus 1,000 for the weight, plus 1,000 newtons. That is going in the opposite direction to my positive, so that is going to be negative 1,000 newtons. Ah, what a surprise, my resultant force is 0 newtons. What you want to emphasize here is that the forces are balanced, therefore the object's motion doesn't change, or we call that floating. The object floats. So it's clear. So that's one case. Now what we could do then is tell a story and say, well, let's imagine that our ship here, while I was preparing for this lesson, I'm doing this in, when is it? June 2023. So one example you might wish to use is something related to the submarine that was just lost recently, going to explore the Titanic. So you can tell whatever story you like here, although yeah, that's maybe not the best example for exactly what we're showing here, because that's nowhere near the surface. But anyway, you can tell a story that this ship, I'm not very well, but anyway, this ship gets a hole in it. And so what happens is it fills with water. And you want to elicit this idea that when this ship fills with water, well, it's going to have a much greater weight, because the ship was full of air here, now it's full of water. So what we're going to do here is show this difference by drawing our thing in the middle here, our dot in the middle, and I'm going to show, well, the weight is increased now, let's say to 2,000 newtons. Again, I'm not drawing this to scale, but weight is now 2,000 newtons. And again, this is a really simple sketch. This is not a perfectly accurate description of what's going on, but let's say, for the sake of argument, that the upthrust hasn't changed, that the upthrust here is still only 1,000 newtons. We take this direction as positive again, and we calculate the resultant force. So I can do resultant force is equal to, that's going downwards and it's 2,000, so that's going to be plus 2,000 newtons. That's going upwards, it's only 1,000, so that's going to be minus 1,000 newtons. What I get here, I'll just move my camera down a little bit. What I get here is a resultant force of 2,000 minus 1,000, which is plus 1,000 newtons, i.e. that's a resultant force going downwards like this, because it's plus, and I've taken downwards as plus. And what you want to show to students is, in this case where the weight is greater than the upthrust, and you've got a resultant force downwards, well, the object must sink. So the boat sinks like that. And again, that's basically it. The purpose of this lesson is that students turn these diagrams that you've drawn into words, and it's about them really thinking about reality in terms of the concepts. In this case, this idea of balanced and unbalanced forces and the effect on motion. Now, what are the misconceptions that are likely to come up here? Lots of students think that for an object to be floating, well, somehow the upthrust must be greater than the weight, perhaps because the boat comes right up to the surface, it kind of gets pushed upwards. So because the water is pushing it up, well, that must be somehow greater than the force that's pulling it down. But that's obviously wrong. And what you want to challenge students to think about, if that's the kind of answer they're giving you, is to say, well, hang on, if there was a resultant force upwards, again, using Newton's laws, what would happen to the boat? Well, it would accelerate upwards. It would start floating in space, and they'll see that that's clearly a bad explanation, and it's about really making them think in a disciplined way. That's what we're all about: disciplining students' thinking. If the object is floating, the forces must be balanced. If the forces become unbalanced, that's going to be why the object sinks. So hopefully you will have some success and really tease out some of those misconceptions that might still be lingering from that kind of intuitive Aristotelian worldview. In the next lesson, we kind of finish off looking at the stationary scenarios, but we're going to look at moments. So it's a slight detour, and then we'll come back to more diagrams like these.